Hi, I'm Leslie Hyatt. I'm a professor at Austin Peay State University, and thank you for watching this video. This video is for instructors, not for students. I wanted to give you an overview of what this idea is that I'm trying to convince you to join me in, and kind of what the components are, and give you a quick overview in this video. So I teach analytical chemistry, obviously, with another professor here at Austin Peay, and we alternate years as to when we teach instrumental and when we teach quant. And so I tried out using these Arduinos, which you're going to learn a little bit about in this video, or you may already know, but I tried them out this past spring, and I was hoping that that would be my pilot, but thanks to COVID, it kind of derailed my plans a little bit. So I want to run another pilot this spring, and then run my study basically the next time I teach it, which would be the next spring 2022. And so what I want to do is I want to invite you to join in on the pilot, join in on developing this project, making it better for all of our students, and then also running the study and hopefully writing a paper on it after we finish it in spring of 2022. So that is my plan. Let me tell you what it is, what my objectives are, what I hope to accomplish with these things, and tell you kind of my story of what happened in the spring. So to begin with, these are an Arduino, and I incorporated them in my instrumental analysis class in spring of 2020. And so before the class started, I invited the students to talk with me about the syllabus. I talked to them about these things, showed them what they were, told them how they could help them learn instrumental better, and then I invited them to help me write my syllabus. They helped me combine the lecture and the lab, because I told them one of the biggest things I don't like about instrumental is it's 3 credit hours for our lecture and 1 credit hour for my lab, but they spend about 90% of their time in the lab with me, and just the 3 hours a week is what they do in lecture. And so we kind of flip things around, and we combined them into a 4-hour course where they worked their butts off in lab. They worked hard in lecture, but not as hard as they did in lab. So my objectives for them to get out of lab is for them to have developed their abilities to be able to go up to instruments and just feel confident that they can figure out the instrument, that they can troubleshoot, that they can do method development with the instruments. And so I wanted to develop their ability to do all this. And what I found is normally in my years that I've taught it in the past, they always do. They get out of it that they are much more confident around the instruments. Not just fake confidence either. Like, they get it. They can walk up to an instrument that they've never used before and ask the right questions and figure out how to use the instrument. But then also method development was huge. They worked all semester designing their own experiments, creating their own methods, and then testing them out and doing their quality control analyses. And so they do a fantastic job of learning all those. But in lecture, I'm a big proponent on getting rid of the big idea of a black box, that this is something you stick stuff in and then out comes data magically out of the other end. I wanted to get rid of that. And so we talk about all the diagrams and stuff in instrumental, as I'm sure you all do. And then I also even have the students take apart instruments in our instrument graveyard. We have one room where all of our instruments go to die. After they died, my students take them apart and they look at the insides. But still, electronics, it blows their mind. And so they think of it as, hey, somehow power comes in and data comes out, but it does all this really cool stuff, and they can understand the physical, what's happening inside the body and how it's all connected, but the movement of current, they don't get it, okay? They don't get how that turns into their pretty graphs that they see. And so I wanted to figure out a way where I could get students to do a hands-on project that would really teach them how do all of that stuff we learned at the very beginning of the semester, how does that transfer into their design of their instruments and better data? And so what I want to do is use Arduinos. And so the students learned it. They throughout the whole first half of the semester. And so with a partner, the students would take their Arduino and they would do lessons. And so each lesson I would guide them through what are the different parts of how do you use an Arduino, what can they use for? And then at the end of the semester, they had a project where they had to design an analytical instrument using their Arduino. And I started them out simple by designing spectrophotometers. And then from there, they had to take it and figure out how to design an instrument of their choosing and collect data with it. And so right about the time of midterm hit was whenever I was releasing them to go create their own assignments. And midterm corresponded with the coronavirus shutdown at our university. And so they were doing this on their home, at their house. And so as you can imagine, the supplies and the chemicals that they can get and their ability to measure stuff was greatly reduced compared with what I wanted them to achieve. But seeing how we don't know how spring's going to go, I think this is a great time to try again, because all the students said, that they learned so much from it, and they were so glad they had this opportunity to use these Arduinos to design instruments. I would see the students regularly in the hallway working on projects that I hadn't even assigned. So it was really fun for me. But then they took it and they made, even though they had limited resources at their house, they made cool stuff out of it. Every single one of them managed to collect data off of their Arduinos. And so this is something that I think will scale. It will be great if we end up going online. This is a hands-on way for them to work with instruments. And so I think going into this semester with the idea that these could be something the students would take home, we can design it more appropriately so that if things happen and we need to virtually use this lab, I think it's very attainable. So that's my story, but I want to tell you more about now how you can join me in this journey, because I do think it's going to really be good for the students. They learned a ton about how electronics work thanks to this. And so what is this and what is the buy-in? So first off, the buy-in, I think I spent probably less than $200 total to get my startup going. I had, and I'll show you these in a minute, I had some pieces that other people had given me before, and so I didn't completely start from scratch, but the main pieces you can purchase based on either bulk items that you buy one pack and it's enough for an entire class, or the actual Arduino itself, which you have to buy per student. So it depends on how big your class is as to how much you're putting in for the Arduinos. But everything here is relatively cheap. What all is there? So this is the Arduino. This is a microprocessor, and so it's not like a standalone computer, the entire everything like you might have with like a Raspberry Pi. You just have a cable that you plug into a computer, so you need the computer in order to see the charts and the graphs and get the data off of it. Also, these Arduinos are about $11 to $13. I got the off-brand ones, the Allegus, for my students. Those are the ones that are about $11, $12, $13. The Arduinos themselves are like $24, so I chose to go with the cheaper one. There are also the Nanos, which are a smaller version of this, but instead they don't have this power cable, and so they can't stand alone, so they can't take it, collect data, and then go plug it in a computer. The computer has to be there during data collection. And so I think whenever I do this again, I'm going to go with the $4 versions of these. But those are kind of your options. But yes, you have a cable, you plug it in, it's about $4 microprocessor. Then I purchased resistor kit, just a giant resistor kit for about $11. Some light dependent resistors. That's just a really simple, cheap detector that we were able to use for our spectrophotometers. A whole bunch of different types of LEDs. I wanted them to see the difference between RGB LEDs, other types of LEDs. I also wanted them to have an IR transmitter and IR receiver, so I bought those packed separately, both of them being about $10. I got some op amps, some operational amplifiers for the students. Like a big pack of these was like $7. A whole bunch of push buttons. I didn't have to buy them because I had enough, but if you buy a pack of 100, it's like $6, $7. I bought some, these are $4. These are little bitty like gooey things that go on the bottom of the Arduino just to keep the pins from rubbing and scratching up the surface of the desktop. And then the other big cost is breadboard. So I think I bought a 10-pack for like $18. So this just depends on how many students you have. You might have to buy 1 or 2 packs. And then you're going to need lots and lots of wires. And so I ended up buying a spool of wires, and the kids can just, you know, cut them and strip them themselves. And then I also made them keep an Arduino notebook where they documented all of their processes, what all of the different values were for the resistors. I made them document everything in their notebook just like they would for a lab notebook as they're designing the process. And so those are all of the components that they need in order to get up and going. And then I'm going to finish making, after this video, a whole bunch of lecture videos that go with the individual lessons. That way they have the worksheet. So I'm going to be giving you the worksheets that the students were working through, plus my edits from the spring based on what the students didn't understand and that kind of thing. And then I'm also going to make videos walking all the students through each one of the lessons. And so what this would entail from you is that over break, you would play with one of them, go buy one, invest in one, and then just play with it. If we live close, I mean, I'm fine dropping one off if you want to just play with some of my supplies. I don't mind that at all. I could make a run to Nashville. But play with it over Christmas break. see if you like it. If you like it and if you can see the value for your class, I would love for you to do this with me. And then when the semester is done, I want to talk. I want to say, what did you learn? How would you edit things? How would you do this differently? And then I hope that before we run it again, we take all of our combined intellect and skills and everything that we have learned from each other and from our students, because I learned a lot from my students, we can combine that together and make a really great study. Because then the purpose of my study is going to see whether or not bringing this back into instrumental is a good thing. It used to be, my understanding, you'd always have to play with breadboards back in the good old days, okay? You would have to play with resistors, capacitors, everything. And so this is just taking technology and combining it with the breadboard, but letting the students do it. They all get to do it individually. And the skills that they picked up, I have just loved watching them grow. And so it's my desire that that this is something that can really help students understand the main concepts of instrumental. And so I want to test and see whether or not that's true. If this is something that could be incorporated more nationwide and more analytical laboratories or lectures. So if this is something you're interested in, just play over Christmas break and then send me an email and let me know if you want to do it. And I'd love to have you join me.